Hello and welcome to ICDD's InSession webinars. Soon you will hear Dr. Jim Kaduk present Ab initio crystal structure solution. Please remember to visit ICDD.com for information on future free webinars, educational events, product information, and to purchase ICDD's databases and software.
Let me add my welcome to everybody to this month's webinar. Ab initio is Latin for from the beginning, and it's the jargon people use to talk about solving the crystal structure from powder data. So today I'd like to give a high level and fairly quick, I admit, introduction to what life is like when your answer isn't in the powder diffraction file. It can be a problem if you want to say analyze a pharmaceutical formulation and find one of the structures you need is not there, but better to look at it as an opportunity to have some scientific fun. So I want to approach it from that standpoint and kind of show you what life is like and some of the resources available to do this. So let's forge ahead. Look at the general size of the universe. If you search the inorganic crystal structure database for structures that are identified as having been derived using powder data, you find that there tend to be 1,000 to 1,500 per year. And almost all of these turn out to be new compositions that are isostructural to a known composition, known structure. Very few of these are actually new structures. I haven't looked at them one at a time to really decide how many there are. But in the organic universe, if you search the Cambridge structural database for powder structures, you see there haven't been very many until the last few years, and we're up to about 200 a year. Almost certainly there are more than that. They just haven't classified them properly, and I do 20 or 30 myself a year, so represent a significant fraction of this. So that's the size of the universe. You might say it's still a select taste, but I want to leave you with the idea that you can do this if you need to and when you need to. You may think you never will need to, but many times in the course of a tech service problem, I've encountered new materials. So I've had to do this, and I choose to look at it as an opportunity rather than a problem. So if you want to learn more about this, I think the best place to start is volume H of the International Tables. This is a completely unbiased recommendation because I'm one of the editors of the volume. But we have a chapter on indexing and on structure, factor, extraction, and all of part 4 of this volume is basically about solving structures from powder data. So it's a good place to start on its own, and it has lots of references to previous literature and examples of this kind of stuff. So a good place to start. The process of solving structures from powder is often identified as a maze. So I've borrowed this figure from Bill David's chapter in volume H, and he's borrowed it from Christian Berlocker and then McCuster. So the idea is we have a sample, we shine radiation on it, we collect data. We have this bottleneck of indexing. Unless we can get a unit cell, you can't really make much progress. Then you extract intensities out of this, determine a space group, have to figure out how you treat the overlap of the reflections, because eventually overlap limits the amount of information you can get. And then we have several strategies for solving the structure, which we'll talk about today. You may not get it all, so you have to complete it. And only then can we do our Rietveld analysis and get the coordinates that we want. And Bill's chapter is basically about bolting on another box to the maze where we can use chemical information. And we'll talk about this when we discuss Monte Carlo simulated annealing. But the maze is a good analogy for the process sometimes. There are false starts and bottlenecks. Another way of looking at the problem is in this figure, also from Bill David's chapter. And solving a structure is an example of what's called a global minimization problem. And the idea of this figure is the z-axis is chi-squared, so the fit of a model to the diffraction data, and this is 2 different translations of a fragment. And the point here is there are huge numbers of terrible crystal structures for any molecule or any chemical system. And then there are often a number of plausible ones that sit at the bottoms of very deep and very narrow minima. And least squares will get you, say, from here to the bottom of one of these wells, but it can't get you from one well to another. So you have to take other strategies to be able to sample all these wells. And it makes it an interesting mathematical problem, but a lot of smart people have thought about it. So we have ways of dealing with it. Several ways of approaching the problem. And the first one is to basically avoid the problem entirely and find an analog. And this is most often done by lattice matching, but also the obvious thing of just doing a search match and seeing if there's something already in the database that matches your material well enough that it could be a suitable model for a Rietveld refinement. But lattice matching is an additional powerful way of doing this. And the tools for doing that are in the powder diffraction file. There are reciprocal space methods where we just use the diffraction data, real space methods where we just use the space of atoms. This slides into the subfield called structure prediction. We'll give an example of that. We can use both real space and reciprocal space simultaneously. So I like to think of this as a hybrid method, Monte Carlo simulated annealing, and this is the most common way of solving structures these days. I still kind of like stealth and guile, where you can use some instincts and experience. And a last way of approaching the problem is really to convert it into a different problem, and that's to consider using a microcrystal. Most of us, I think, are used to the idea of sieving our powder through a 325 mesh sieve. Well, that's 45 micron opening. And given the improvements in single crystal instrumentation these days, I see single crystal structures determined on things about that size. And certainly at a synchrotron, one could do a single crystal structure from a 5 micron crystal, the kind of thing that we'd normally like to have in our powder. How one mounts and centers such a thing is an interesting concept, but you can also imagine looking at a small assembly of such crystals, polycrystals. And the idea would be to essentially collect the data set from each individual crystal in your specimen, and then merge all those together into one single crystal data set and solve the structure that way. You might end up getting a better refinement by the Rietveld technique using the powder data, but getting the initial model might be something to consider doing it this way. This is talked about more often than it's actually done, but it's something to keep our eyes on. So let's forge ahead. Mentioned indexing. Without having a unit cell, it's tough to make any progress. And indexing could be the subject of its own webinar easily, and perhaps we'll schedule one someday. But the short answer is that indexing is all about obtaining accurate peak positions. And if you have accurate peak positions, the indexing algorithms will generally work well. If you have inaccurate, wrong peak positions, especially with a systematic error, you have trouble. So it's all about accurate peak positions. So this slide is a reminder to me that I want to just fire up Jade, which I have here, if I can click it. And what I have here is I've read in a synchrotron pattern of a molecule called elvitegravir. It's a pharmaceutical that I've worked on in the last few weeks. And as I mentioned, indexing is all about, oops, I don't want an arrow, I want to zoom. Zoom. All right. Gave me, excellent, much better. Okay, so it's all about accurate peak positions. So Jade has located peaks when it has read the data in, but it's worth a little manual looking to see if it uses the right peaks. And in this case, it has found some artificial ones at the low angle backgrounds. I'm going to delete those, and the peak 1 and 2 are from the Kapton, and now we can look at real peaks. Normally, I might, on the first pass, ignore this weak one at 0.6% relative intensity, but it turns out this was an important peak in this problem, and sometimes you have to try several times. Normally, might tend to ignore the very weakest peaks, say less than 1%, try to find a unit cell. And then if that unit cell accounts for those peaks, you feel pretty good about them, that they are real. There's always a question about whether you have an impurity or not. And the idea is if you can describe the positions of all your peaks on one unit cell, it's real strong evidence you have a phase pure sample. Conversely, if you're trying to index a mixture on a single unit cell, it's a hopeless exercise. So I just want to scan a few more of these peaks. That one seems like a real peak, but we'll leave it there. Okay, so indexing in JADE under the start menu, and there's pattern indexing. But before I forge ahead, I wanted to point out that there's this newish item called MDI Toolkit, and that includes a charge flipper and solving structure options. These are pretty new. I haven't had time to explore them fully, and we can expect them to develop in the future. So it's one of these stay tuned kind of things. So you have tools already, and you may have such tools already at home buried in your software, that some of the packages do have tools for doing this. But I want to focus on the pattern indexing at this point. It suggests there's a possible zero offset of 0.003 of a degree. Okay, I'm not going to worry too much. It starts being hundredths of a degree. It's a sign there may be a systematic error. As in always in JADE, there are lots of controls all over everywhere. I'm just going to use kind of my default ones, but go into the seek. I'm just going to look for cubic through monoclinic cells and using the quick indexing. For orthorhombic and above, JADE uses its own algorithm, which I conclude is kind of a Trayor-like algorithm, but perhaps the guys can correct me on that. But for monoclinic and triclinic, they use the ITO algorithm, a different way of doing it. But in this case, I'm just going to hit seek and just let it run for the few seconds. It has come up with a monoclinic unit cell, very good figure of merit in JADE's figure of merit, really good figure of merit for Smith-Snyder figure of merit, no unindexed peaks. It suggests symmetry. In fact, this is a chiral molecule, so it can't be P21 on M, but turns out to be P1. This is the right unit cell, but you note that the beta angle is very close to 90 degrees. Initially, I made the assumption that that really was going to be 90 and that this the structure was orthorhombic and could get a plausible structure solution out of it, but it wasn't really satisfactory. The volume is such that there are 4 molecules in the unit cell, which is nice for an orthorhombic, but it turns out that this weak little peak is 001, and that violates the orthorhombic symmetry. So it really is monoclinic, and it really is about 90.03. You know, JADE was really right. I didn't really trust it that much at the beginning, but turned out to be right. It just means there are 2 molecules to find instead of 1. But with really good data from a synchrotron, indexing can be really straightforward. So I got to start you with a good example. I want to switch over for a second to the predict interface from ICDD. This is one that ICDD has written to be a graphical interface to the Dickvall indexing program, so a different algorithm. So I want to just import the same diffraction file, which I know is this one, and I have some synchrotron defaults, and again, it would normally be worth looking at the peak list a little more carefully, but we'll just run Dickvall. I do want to include monoclinic here. I find it useful to include the possibility of an impurity line. There always seems to be one line that's located less precisely than the other. And I'm going to add a 0 correction and just run Dickvall. Dickvall is much more numerically intensive, but can be really useful. Now we have 20 out of 20 peaks indexed with a really high figures of merit here. It finds an orthorhombic unit cell, which is the same dimensions and same volume. That turns out to be slightly incorrect. It also finds a monoclinic unit cell with a different volume, and that it's a much lower figure of merit, still fairly high, but that one turns out to be wrong in the sense that it doesn't let me solve and refine the structure. ultimately, if the cell is good enough to solve and refine the structure, it's good enough. And when two or more indexing algorithms give you the same cell, you start feeling a little more confident. So let me go back to Jade for a second and pick another example. This is, again, one that I'm working on currently. This is a sample from Wanging at NIST, and thinking this turns out to be the type. I hope you can see it. It's hidden under a control box, but it's a barium, strontium, titanium, niobium oxide. The peak list at first glance looks pretty good, so I will just pattern indexing. It suggests there's a really large zero offset. This pattern was collected on the zero background cell, which almost certainly means that it has a displacement error. I'm gonna just proceed here. Yeah, we'll just do the quick indexing again, and then let it work through things. And in fact, it has found a C-centered orthorhombic unit cell, which turns out to be the right unit cell. The suggested space group turns out to be incorrect, but that sometimes happens. But once you find a unit cell in the powder diffraction file under the crystallography tab, you can search author's unit cells to do a reduced cell search and see what compounds match. Of course, before doing that, you would just do a normal search match and see if there's something that's suitably similar. But the cell search provide a complementary way of doing that. So in this case, Jade overcame the displacement error. I'm not going to bother showing you predict-dickfall because that 1/10 of a degree error is fatal. That program will fail. But to emphasize the point that you want accurate peak positions. And the best way to do that is to add an internal standard and get exact peak positions. Okay, so enough about indexing. Let's go back to, let's go to full screen. Okay, so I want to switch over to reciprocal space methods. One can use Patterson methods, some of which are buried in this program called XLens, but it's really a direct methods program. There are maximum entropy methods, which I've never used because I've never been able to get my hands on this software. Most commonly, we're talking about direct methods and charge flip. Direct methods are traditional direct methods where you have a set of structure factor amplitudes derived from your intensities and use probabilistic relationships among the phases of strong reflections to generate a set of phases. This is what single crystal people do all the time, and this is a good place to get the details on that. Charge flipping, I'll give you some references a little later. So direct methods. One can use single crystal direct methods by essentially creating a small kind of crummy pseudo single crystal data set from your powder data. I find it more efficient to use a program designed to do this. I tend to use Expo 2014 from the group in Bari. I mentioned the XLens program from Jordi Rius. Also will work well. These are designed to work with powder data to overcome some of the limitations of overlap and limited data, and can work reasonably well. So an example, this is lithium dipotassium citrate monohydrate made by my former student Andy Sigler at North Central College. So here's the data. This is a little unusual data because it's measured with molybdenum radiation. And I have put it on a square root scale. And both direct methods and charge flipping generally need what's called atomic resolution data, in the sense that we need good, in the sense of accurate intensities at despacings 1.3 to 1 angstrom. So with copper radiation, 70 to 100 degrees. A lot of times we don't have that, so the direct methods will fail. But these little wiggles are not noise, but they're individual peaks. And the fact that I could fit these, well, meant the direct methods work. This was very easy to index with Jade. On this orthorhombic unit cell, the volume is small and it corresponds to 2 formula units instead of the 4 you would expect from this space group. So we already know something that is interesting, and that some of the atoms sit on special positions, which we can see in the next. So basically turn this loose in the Expo program, and it after a couple of minutes, this picture shows up and we find the citrate sitting on a mirror plane. We find the potassium, that's easy because it's heavy. It actually found the lithium, which it called the carbon atom, but that's easy to fix manually. And it found the water molecule also on the mirror plane. And this took just a couple of minutes. Doesn't always work, so sometimes you have to just try it again and see if it partitions the intensities a little differently. But again, we start with, give you some confidence with an example that works, but this is laboratory data. Another example, a molecule of this Monte, which is a pharmaceutical I've worked on recently, and it's used to treat basal cell carcinoma. This is a synchrotron data set, part of a project that we have with ICDD headquarters to get good reference data into the database. So here's the molecule, easy to index with JADE Pro, primitive monoclinic unit cell, a space group is P21 on C, and I take that information, throw it into Expo, and within a couple of minutes, here's the molecule. It doesn't actually get all the atom types right. This is a chlorine, this is a sulfur, the bond is a little longer for it to draw the bond, and then you have the challenge of deciding which two of these are oxygens and which is a carbon, but that you take care of during the refinement. But once it gets the connectivity right, and you know the molecule, you can easily change the atom types. Then I got a good refinement out of that, and then compare it to a density functional quantum mechanical calculation. So the Rietveld is in red, the DFT is in blue, and the average deviation of the atom positions is 600ths of an angstrom. The orientation of the methyl group from the Rietveld is different than the quantum mechanics, but you don't really expect to get that right with X-ray powder data anyway. But this gives me confidence the structure is right. And there's the structure just for fun. I have to show some crystal structures here. Okay, I want to switch to charge flipping. And so just look at the references. A much newer algorithm, given the references. And direct methods are magical to me to be able to get the phases out of the intensity. Charge flipping is a different order of magic. I'm not quite ready to say it's dark magic, but it seems especially magical. So the idea here is that we have a set of structure factor amplitudes from single crystal or powder data. We assign them random phases and then Fourier transform them to get an electron density map, which is complete nonsense because we have random phases. But the map has positive and negative regions of electron density, and we know that real crystal structures have to have positive electron density. So you mathematically convert the negative density to positive density. That's the flipping of the charge. Have a new electron density map, back transform that to get a new set of structure factors, amplitudes, and intensities. Throw away the intensities because we think we've measured those, but use the new phases and keep repeating the process until it converges. And how can this possibly converge? But it works, and has been used to solve some quite complicated structures. I generally do my charge flipping in YANA. People raise their eyebrows at that. This is the program that's generally used for incommensurate and modulated structures, but I find its interface congenial for doing charge flipping. And charge flipping is buried, I should say, incorporated into many programs. JADE, GSAS, Topaz, I think even HighScore has charge flipping buried in it. So you may have the algorithm at home to try on your own data. But I tend to do it in this program. So here's one example, flucytosine, a simple antifungal pharmaceutical. So this is synchrotron data from 11VM at Argonne, indexed it with the N-Traor program that's buried, incorporated into the Expo program. And it is tetragonal, strangely enough. That was a little surprise for a pharmaceutical, but it solves easily by direct methods and charge flipping. And there it is. Again, the program misassigned one atom type, but knowing what the molecule is, it's easy to correct that before you do a refinement. But in this case, the structure solved even before I had time to do a reduced cell search in the Cambridge database. And was disappointed to find out somebody had already done the structure. So I didn't have to do any refining. We could just prepare a pattern, and now it's incorporated into the powder diffraction file. So you can identify this compound if you ever encounter it. But it worked very well. And the key was we have good intensities, accurate intensities out in this range. When the pattern dies by 20 degrees at the synchrotron wavelength, you know you're not going to have much success. Direct methods and charge flipping from synchrotron data like this on an organic material work 15 or 20% of the time. So most of the structures I solve are from Monte Carlo simulated annealing, which we'll talk about next. Not quite next. We've got a real space example. This is trimelitic anhydride. This is my past life at Amoco and BP, where my colleagues made 120 million pounds a year of this stuff. So it's 1,2,4 benzene tricarboxylic acid, 1,2 anhydride. It's a chemical intermediate. It gets used cross-linker and all kinds of other places. I was always a little embarrassed that we didn't know the crystal structure of our commercial product. This is really a structure prediction exercise. And generally out of an exercise like this, where you take a molecule and don't assume a space group or unit cell, but try to use force fields and or quantum mechanics to try to optimize the crystal structure. Here's an old issue. Generally out of this, you get a library of crystal structures, very similar in energy. All of these are within kind of the expected error of energy, and they're just sorted by density here. And knowing each of these crystal structures, you can calculate a powder pattern. That's the easy part. And it's easy then to tell that the right structure, the observed structure, is this one. What are all these other things? Are they just undiscovered polymorphs? It's an interesting question that pharmaceutical people have to worry about. But the idea is you get a library of structures, and it turns out then you don't need very much diffraction data to distinguish the right one from the wrong ones. So here's the Rietveld refinement, sort of do this backwards. So here's the fit. There's 4 sets of tick marks here, one for the anhydride, one for a silicon internal standard, one for corundum from the micronizing mill that I used to grind it, and a 4th set of tick marks, which turn out to be trimelitic acid. Between the time we got this from Chicago to Brookhaven, where this data was collected, a little bit of this reacted with moisture in the air and hydrated and made the acid. It's an annoyance, but it's just another phase, and it's not a serious problem. So every time I tried to grow single crystals, I made adducts, and that's a different story. But it was very easy to index the laboratory pattern, the synchrotron pattern, on a primitive orthorhombic unit cell. And I could tell that there was a 2-1 screw axis parallel to the A axis. But all the peaks that I wanted to use to determine the symmetry in the other directions by overlap, by other reflections. Mother Nature was a little unkind here. So there's 7 possible space groups here, but 3 of them are very rare. So we limited our universe to 4 space groups. From the density, which we know from the commercial product, we know there are 4 molecules in the unit cell. And any organic chemist would tell you that the free carboxylic acid here would make a centrosymmetric hydrogen bonded dimer. But there aren't any centrosymmetric orthorhombic space groups with 4 molecules in the unit cell. So we already know something interesting is going on. Sometimes useful to think about early in the process. Anyway, the process is more complicated because there are really 2 different conformations of the molecule. These are different shapes and would pack differently. So we had to consider them separately. My quantum mechanic colleague, Joe Golab, did a high-level molecular optimization, and we fixed it. So we basically used 2 conformations, 4 space groups, so 8 structure prediction runs, and generated a library of potential energy structures. This took about 3 weeks of computer time on a big silicon graphics workstation. So it's a lot of computer power. But after all this, looking at the results, the second lowest energy structure in this common organic space group had a cell similar to the observed one, and that was I used to refine the structure. The structure contains helical hydrogen bonded chains, kind of zigzagging along here. And if you look down the chains, which are here, you can see there are CHO hydrogen bonds. And people used to argue about such things, whether they were real or not, but they're real. And this is a fairly old example that you could read more about it and some of the solvates that I made trying to grow single crystals. Okay, the state of the art of structure prediction is this program called GRACE from Avant-Garde Material Simulation. I haven't used this one yet because I don't have a computer at North Central College that's big enough to run it. It needs at least 128 processors to run, and the chip shortages are real. So we're waiting for a new server to try to run this. So stay tuned. Okay, now I want to switch to finally what are often called real space methods, but I like to think of as hybrid methods. The name is Monte Carlo simulated annealing, sometimes called parallel tempering, related but slightly different algorithm. The idea here is that we assume we know a unit cell and we know a space group. We may have to try several possible space groups, but the key is that we know a unit cell. And we also know the chemical connectivity of our molecule or our fragments. So the idea is we drop our molecule in a random position, random orientation, random torsion angles, and calculate a powder pattern, which again is complete nonsense. And then we change one of those parameters. The jargon is to make a move, calculate a new diffraction pattern. If the agreement with the observed data gets better, we keep going. If the agreement is worse, we mostly throw out that move and try something else, but we do accept it with a finite probability that decreases throughout the process. And the mathematics of that is the same as the mathematics of annealing, hence the simulated annealing. The Monte Carlo, of course, is the randomness. Basically, this is a fancy name for guessing. You know, it's Monte Carlo simulated annealing sounds pretty sexy, but we're going to guess millions, tens of millions, hundreds of millions of times until we can get the best fit to our data. Computers are good at that sort of mindless activity, and you normally do it many times and see how reproducible the structure is. You know, it doesn't really matter if the computer fails hundreds of millions of times, as long as it succeeds at least once. I mean, we ourselves don't want to be failing that many times, but okay for the computer time. So for one example, a rubidium hydrogen citrate. I like citrates, so I've had students work on these. This is yet a different student looking at alkali metal citrate salts. So here's ordinary copper K alpha data. It's off the Brooker D2 that we have at IIT. So perfectly ordinary data, same as you would collect in your own laboratory. Here the indexing was a little ambiguous, that we had to try both orthorhombic cells and monoclinic cells. The indexing was complicated because this was measured on a zero background cell and had a large displacement error. Would have been better to collect it with an internal standard, but we didn't bother doing that. Ultimately, after trying several different space groups, it looked like the space group was P21. So we did the Monte Carlo simulated annealing using 2 rubidium atoms, a citrate fragment. And this is before we knew any bulk analysis. I included an oxygen atom for perhaps a water molecule. So used 2 other programs to do the simulated annealing and then refined it in GSASS, and the water oxygen moved way too close to the citrate. So it was clearly artificial. I just removed it. So it was anhydrous, and we could confirm that later. The key question in such a structure like this, something I'm interested in, is where is this hydrogen, the unionized carboxylic acid group? And in this case, we got lucky because there's a pair of oxygens that are about 2.4 angstroms apart. So there has to be a proton. The jargon these days is that's a charge-assisted hydrogen bond. So we know there's a hydrogen in there, and we let the quantum mechanics decide which oxygen it was on. It was very easy to tell roughly where it was. And then got a really good refinement, and then did the quantum mechanics, which agrees very well. We got 2 structures overlaid, and the quantum mechanics decided it was over here. I just put it halfway in between to start the refinement. Let the DFT move that around. Okay. Another example, a newest one here. This is a pharmaceutical called cynorine monohydrate. That's easier to say than 1,5-dicathioyl quinic acid. This is of interest these days as a HIV drug. So while we looked at it. So if you go to the PubChem website, you'll find the 2-dimensional structure of the molecule. And we have unspecified stereochemistry about the double bonds and the 2D representation. But the 3D representation they give you has both of the double bonds being trans. So start with that. So again, synchrotron data from 11DM, very easy to index with JADE, 2 molecules in the unit cell. I solved it with yet another program called FOX, using that fragment I showed on the previous slide. But also, since I wasn't sure about the stereochemistry of those double bonds, I broke the molecule here and used this fragment and this fragment and this fragment, and they reassembled themselves into trans double bonds. So that picture was right. But the first time I did this and then did the DFT calculation, the agreement is outside of the normal range of correct powder structures. almost half an angstrom difference in the heavy atoms. So it's a sign that this is maybe close, but not quite right. So I just did more simulated annealing runs. The first structure was somewhere in here. The Fox calculates a cost factor, lower is better. So I was in here, but let it run many more times. And there were a couple of really very much better structures in the sense they fit the data much better. So sometimes your success rate on a simulated annealing is fairly small, maybe to 1 or 2%. So you end up trying lots of runs, but if you succeed once, that's enough. So again, the right one turns out to be way down here, whereas I was using something out here. Got a much nicer refinement. The structure agrees with quantum mechanics much better, but there's a hole in it. And it's perfectly located to be a water molecule that will hydrogen bond to a couple of hydroxyl groups. So we did NMR and TGA to confirm its presence. And then this is what the structure looked like. All the hydrogens, or all the hydrocarbons sort of fits in layers, and we have these hydrogen bonded layers. And it's always very gratifying when the journal editors think enough of it to put it on the cover of the virtual issue of the journal. So this is just from February, February of this year. But that was a fun one. I have a couple of minutes to do stealth and guile. So here's an example: diammonium salt of 2,6-naphthalene bicarboxylic acid. It's an aromatic acid that my industrial employer has made. Not very soluble. And I remembered my freshman chemistry that ammonium salts were soluble. So I could learn how to make this by taking ammonia vapor, reacting with the acid and making this material. I couldn't actually index this until I took it to the synchrotron. And then it became interesting because if you search the Cambridge database for kind of compounds like this, you expect they have a density about 1.6, and this is 1.4. So it was lower than usual. It's kind of interesting. Anyway, so I collected the data in 20 minutes. And once I had this cell, I realized it was about one NDA long, one wide, and one thick. So it's a centrosymmetric anion. So I assumed space group P1 bar, put it at the origin, manually adjusted it to orient it, long, width, high, so that they didn't overlap. And there was a hole. So I put the nitrogen for the ammonium there and refined it. And it took about that long, actually. It was pretty simple. There's the refinement. There's not very much data there, and the peaks are really very broad, which is why I couldn't index it at home. And I've given you a space filling rendering here, because even here you can see there's empty space. So we have an open network of very strong NHO hydrogen bonds. This is less dense than you would expect, for the same reason that ice is less dense than water, this network of hydrogen bonds. So that was a fun thing, just using my chemical intuition. Once I had a unit cell, if I hadn't had a unit cell, it would have been a lot tougher problem. Okay, one more example. 1,16 hexadecane dioic acid. This is an example of a set of long chain dicarboxylic acids that I worked on a few years ago. The structures were known until C10, but the longer ones were not. So here's an example. The black curve is an experimental data on a square root scale to emphasize the weak peaks and to emphasize there really isn't very much data here. This green one is one curve calculated once I knew the structure, and the square root scale means we have these cutoffs here. And patterns like this are very difficult / impossible to index because there are not very many peaks, and there are even things that look like single peaks turn out to be many peaks. So you don't really know what indices to assign them. It's only after you have a rough model that you know the indices of this peak and then could calculate a better unit cell. So it was kind of a perverse problem. From the small, shorter chain ones, you know the structures are going to be something like this. And so the strategy I used, which turned out to be more difficult than it sounds, because of course you know the cell gets longer with longer chains. So I oriented it this way so that the chains are basically kind of zigzagging in the plane. We have hydrogens up and down. I basically broke this bond in the center of the chain, then increased the cell dimension, and did this starting short and then going longer, and then stuck a couple of extra carbon atoms in here, then did a force field minimization, and then did the quantum mechanics, and then did the refelt refinement. So did it backwards from the normal order. And looking at the patterns, you can see the cell gets longer as the chain gets longer. And we have these kind of polyethylene features here, but the rest of it is not all exactly the same. There are subtle differences in the structure. And you could see some of that, whereas the cell along the chain gets longer with carbon number. Some of the other edges and angles show more interesting behavior. And ultimately what happens if you look down the chains, you see they twist. I'll wave my hands. They twist slightly, and not all the torsion angles in the chains are 180. There's some subtle variation. So it's kind of a fun systematic series, but it was fairly challenging because none of the normal approaches would work. We had to base this on what we knew had to be the case from smaller molecules. Okay. If you want to do this, there are lots of resources available. I mean, I neglected to put Jade, of course, on the chart here, but we'll shamelessly plug that. Some of these are free, available to everybody. Some are free for academics, like the Expo program. If you're industrial, it would be €1,000, worth every penny. The charge flipping, as I say, is buried in many programs these days. So you may actually have it at home. Some of these are free. The DASH program used to be with the Cambridge database, but is now free. Some of the commercial things can be quite expensive. It's worth having a variety of resources available because sometimes, just like with indexing, one program will work and one time and not another. So you really want to have a variety of tools to apply to a particular problem. And as I've mentioned, even the direct method sometimes doesn't work one time and will work again. So you always want to try even the same program multiple times because you only need to succeed once. You want to know a little bit more about this topic, I guess I can say stay tuned. Coming later this year will be this chapter on ab initio structure solution using synchrotron powder diffraction in a reference work called Comprehensive Inorganic Chemistry 3. My understanding is that electronically this will be available later this year. I haven't seen the proofs of this chapter yet. And then there'll be some print books next year. And I've given, since it's inorganic examples, I've given lots of inorganic examples using the various different methods here. So stay tuned, I guess. At that point, I think I am done. So let me at least shrink that. Perhaps I should where is my unshare? Pause share, perhaps?
Probably at the bottom. Probably at,
yeah, well, it happened to have moved to the top. Now it's there. Okay, so now we're back. If your head hurts, that's okay. I wanted to go fast and give you a general flavor of what's this like, but you really want to have good data, so you can get good peak positions, good intensities, and you do need some extra tools, some of which you may have, other which you may have to acquire and learn how to use. Just what you need, one more learning curve. But anyway, I should shut up and see what kind of questions you have.
Thanks, Jim. It's funny, it was fun going through the attendee list. You have some friends out there and maybe even a few fans, so that was fun to scroll through there and chat with folks. I should say my name is Scott Cole. I am the sales and marketing manager for the ICDD, and I'm based out in California in the ICDD's Livermore office. So let's see, we're coming up on time. So I will jump into the questions, Jim. There were no shortage. This is an active group of attendees. So
okay,
let's kick it off. First one is, can I use an ICDD PDF database to get started with isostructural analysis to help with indexing? And once I have that information, can I use Jade for additional analysis?
Okay, well, I can be flippant and say yes, 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 and yes. Now let's give the real answer. I should start by saying the obvious thing. I mean, before you attempt any of this sort of activity, you want to just do a normal search match and see if something matches, something of similar or analogous chemistry matches your material well enough to serve as a suitable model. I mean, I'm thinking like the same formula type, maybe two big cations, some tetrahedral anions. It's just the chemistry is different. And if that doesn't work, a next and alternatively and very powerful step would be to index the pattern, get a unit cell, and then do a unit cell search in the PDF. And this is under the crystallography tab. It's a newish feature just in the last few years. And see what compounds have similar unit cells. And the reason that this provides an alternative way of finding an analog is that atoms vary less in size than they do in scattering power. So the intensities of isostructural materials, the peaks of the patterns of isostructural materials will vary more than the unit cells. So the cell just uses the positions reduced to a unit cell is really an alternative way. And I could perhaps even someday give another webinar on that working by analogy, because that's been a very powerful approach for me over the years. So you fairly get in the idea of you find a vanadium compound where you have an iron or you have an aluminum one instead of a chromium one, stuff like that. And those are often good enough models to start a refinement. But certainly do a traditional search match first and then start doing the more elaborate things. And only if none of those give you a model, then you start trying to solve the structure. It's a last resort or plan B or plan C to try to solve your problem.
Understood. Thanks, Jim. Okay.
The last, so that was database. And then of course, one could do the Rietveld refinements in Jade. Once you're done, you probably have noticed I tend to use GSAS because I doing a lot of organics these days where I really do need constraints, restraints, and rigid bodies, things that haven't quite showed up in Jade yet. Hint, hint.
There you go. Stefan and Rongshanger here. So
yeah, that's right. We might as well be shameless about this.
That's right. Okay, here we go. So there are some solid solutions, alloys, for which the XRD patterns are not available in the database. Is it possible to submit the XRD data we obtained experimentally to the ICDD database?
Okay. Again, the short answer is yes, but there can be an it depends. The ICDD is producing this database for phase ID. So if the patterns are different enough to be useful in phase ID, they'll certainly be interested in them. It'll depend on how different they are. Many times, I tend to think in cell volume. So the cell volume will vary by a few percent over a structure, over a solid solution series that shifts the peaks enough that they would be outside of kind of normal windows that you might apply in a search match. So if they add extra content, both in terms of the pattern itself, headquarters will be interested in, but also if they include chemistry or chemical differences. So if it's new chemistry but has a pattern that looks very similar to something else, you would miss it perhaps if you were limiting your search by chemistry. So headquarters is always interested in new compositions with similar diffraction patterns. Ultimately, that's an editorial decision, so I can't give the final word, but I can give you the kind of general philosophy of things, that if it will be helpful to identify compounds, we'll be interested in including them to the database. So if you can't identify your compounds with the existing universe of database entries, they should be by definition interested of useful to you and presumably other people. So I think there'd be a bias to include them.
Right. Okay, here we go. Next one. Which is the criterion for selecting the program for doing the crystal structure solution?
Well, it's a good example of the idea that there's only one answer to any question about powder diffraction, and that is it depends. But I will always try direct methods and or charge flipping, which tend to be about equivalent in their success rate, partly because they don't require any thought or say biasing by assuming a chemical structure. As I mentioned, for organics, you do need atomic resolution data, so they succeed 15 or 20% of the time. For inorganic systems where you really do have atomic resolution data, say good peaks at higher angles, the success rate is higher. So I'll try those, and if they succeed, great, then I can go and do my refinement. If not, then I'll have to take the trouble to find or build the molecules and then go to the simulated annealing kinds of techniques. And if I'm going to use simulated annealing, I often will try multiple programs simultaneously. So it's fairly frequent. I'll have one of my cores running on Expo, one running Fox, one running Dash on the same structure, and then whichever succeeds first, I'll go with that. So sometimes I get asked by a reviewer of a paper, well, this time you use this program, last time I used another program. Well, I figured I'll report the one that worked and not the one that didn't. So that's why it's useful to have multiple tools, because sometimes one will work and one will not for reasons that I'm not smart enough to understand.
Well, that explains the population of icons on your laptop.
Oh yeah, exactly. They're there because I need all those tools.
Okay, so we have got another one here. Are the Rietveld refinement results obtained through Jade comparable to those with full prof suite or any other refinement tool?
Well, since ultimately you're trying to do the same mathematics, they should be. And when I have compared, they have been.
Yep.
So, I mean, you would expect some variation, I think, just for almost statistical noise. If you come to my workshop on quantitative analysis at DXC, I will indeed show one example where the quantitative analysis out of Jade is the same as out of GSAS.
Okay.
So, and when I have done such comparisons, the structural results have been very similar. I should probably say insignificantly different would be the weasel words.
Yeah. Before I pass back to Steph, I want to say that early in the presentation, we got a few questions asking when you would cut away to use Jade. People were questioning, what version of Jade were you showing, which was Jade Pro. So I guess I just wanted to say in general terms, if you're using Jade and it didn't look like what Jim was presenting today, certainly contact us, our office, and we can send you information about converting what might be a classic Jade license into the more modern interface of Jade Pro or Jade Standard. And with that, I will say thanks very much, Jim. That was a great, informative presentation.
Don't forget to like and follow ICDD on Twitter, Instagram, LinkedIn, and Facebook. More information on ICDD.com. Contact us at info@icdd.com.